Okay, welcome back, everybody. Let me just take the in-class attendance really quick. Yep, thank you. Oh, don't worry about the paper anymore. You don't have to. Okay. Yeah, that's it. Okay, so small class today, and also 5 people online. That's fine. Before we begin today, today's what? Unit C5. Here we go. Unit C5, yeah, that's right. We completed Unit C4 in last class, and then today we are going to take a look at C5. That means this is an example of performance calculation. So that literally means that the phase 3 of your project is coming near. Okay, so let's just talk about, we have updates. Nothing new here. I think you're working on homework C4, which is due Thursday, April 15th. Have you done it? Jimmy, have you done it? Because I accidentally sent you lots of information for you to see.
I finished it.
I didn't realize it. Okay.
Yeah, after you sent me that one, I was like, that's not what I need to check my homework with.
That's right. Yeah, sorry about that. I cannot take it back anymore. So.
No, because I tried to check my answers with it, and I was like, all my answers are wrong. And I was like, oh,
well,
it's not
then you realize, hey, this is not the
Yeah.
answers for C3. Well, you gave me C4 already.
Yeah.
Oh my goodness, I didn't mean to.
Oh, I'm done.
So
I
that
don't
means,
care.
yeah, that's fine.
I
As
want-
long as you're doing your work, that's all that matters. This is not the error 1. Error 1, it matters, of course, yes. I'm a super sticky, strict, and then monster professor in error 1. I literally try to flunk anybody who is not qualified, because that's the block of people who should be giving up error track major. That is error 1. You went through it already. Congratulations. So you're just having fun from now until you graduate. In my mind, yes.
I don't know if it's fun. We'll see about that.
Yeah, but you know what to do. You know how to do it.
Yeah.
It's easier to handle for me. I don't have to tell you, okay, so this is the not right behavior as an engineer. You just don't show up like 2 months and doing nothing, and then all of a sudden, hey, I want to audit. Do you understand the meaning of audit? First of all. Yeah, today I went through lots of conversations just like that.
Oh, I
Well, you didn't participate like past 2 months. You just didn't do anything, and then all of a sudden you said, "Well, I want to audit." What do you mean audit?
What's the difference?
You can drop it, of course, sure, but what is audit? Audit means you still want to run something. Do you want to run something? I don't think so. So I basically denied the multiple requests of audit today from error 1 class. Only thing they can do is withdraw, because it's the same thing, because that's what they did. Okay, they don't want to run it, they don't want to do anything, just withdraw it. Not to audit, just don't use the fancy term to do something different. So I'm going to behave like that in error class, not here, because you guys not going to do that. You went through that stage. You're getting ready for professional engineering and getting into the business, so I'm focused on that. So anyways, having said that, I'm not going to postpone those things, okay? Because of the reason I just said, I'm not going to postpone homework C4 due. It's Thursday, it's as it's written. And then quiz 5, of course, I hope you're working on quiz 5, right? And I received a couple of very good questions. Who actually gave me a question? Josh? Okay. So he gave me very good questions, and then we sort of thinking through about that, and you're absolutely right. Yeah, so you're doing a great job. I assume everybody else is also doing a great job, so I'm not going to postpone this.
Wait, what question is this?
Quiz 5. Quiz 5, well, you are in the same team. No, it's not.
Wait, what question?
What question? Go ahead, share. What was the question you asked for? You asked today, Josh?
I was asking about the CD naught in the takeoff constraint.
Yeah.
Because it showed it in the example in the notes.
That's right. So this is the constraint analysis, and then these are the constraints: super cruise, combat turn, horizontal acceleration. All of those requires aerodynamic drag polar information, which includes CDO, which is parasite drag. But if you constrain takeoff of course requires CDO information, isn't it? But it basically says T is way bigger than D. So this actually indicates that, well, thrust is strong enough, so you can essentially ignore the drag generated during takeoff roll. And then I literally took that meaning, and he had doubt about, okay, can we really do that? And then I said, well, why don't you plug in CDO information into the takeoff constraint, see how much impact do you have? And then he reported back to me, there's not much impact. So CDO equal to 0 is about the same result unless you have an airplane with CDO equal to like what?
It was one.
CDO
is equal to 1, but when it started actually.
CDO equal to 1 means probably your airplane is like a flat plate perpendicular to the direction of the flow. CDO is 1, yeah, could be. It's like a signpost. Yeah, it's a huge drag, of course. Yeah.
Sure,
If the flow is perpendicular to it, everything is stopping. The flow is all stopped up, CDO is 1.
Yes, thank you, mistake.
It's not airplane at all.
Yeah.
So again, yeah. So that's a very interesting discussion today. I enjoyed. So I appreciate that.
Okay, good.
So everybody is doing this and hopefully doing good job because this is, look, 50 points. Okay, this is 50 points. It's a huge impact. Okay, so you can either recover whatever you did poorly in the past, or you are going to completely screw up your quiz. Either way, you know that. I don't have to emphasize. Okay, so please do that, and then do the exercise day period. I'm not going to push back. Okay. All right. Of course, you're working on it. No, I don't worry anything about it. This is not the other one. Any question? Any comments? People online also. If you are perfectly happy about what I just said, please express yourself. And there's no negative reaction here. You have to complain to Microsoft Office saying, well, you need to have some negative expression, like a thumb down, not the thumbs up, or boo kind of thing. Too bad you cannot do it right now as of today. Then Microsoft will listen to you. If we need a negative reaction to the Teams online meeting, you should implement something like that.
Microsoft listens to its customers.
Okay, so hopefully you're doing okay too. You're online. If you have any question or anything, just unmute your microphone or react or whatever. Okay, just to tell me. Jordan, did you fix your microphone problem?
Yeah, it was a USB port issue.
Oh, good. I can hear you now. Okay, good. So let's just move on today. Today is going to be, okay. Let's just take a look at course materials quickly. So today we are going to probably cover up C5. C5 is fairly short unit. Everything is just an example for your project. So next thing to come is, of course, the phase 3 of the project. When do you want to complete this one? Of course, phase 4 is a final day, which is Monday, May 3rd.
Oh, sorry.
Today is April what? So,
13.
13. Half of the April is already passed. So when do you want to complete phase 3? I want to hear first from you, and then just to set it up. There's not much room to push back, though.
Next Thursday?
Next Thursday. Can you do that? I mean, this is very good calculation. I mean, after you went through today's lecture, you realize, wait a minute, do we need to do this much? Are we ready for it? Kind of reaction may come up.
Are you saying we don't have enough?
Huh? Yeah. First of all, you need to come up with like a thrust curve or power curve or both. And then based off of that, you're going to compute the performance. And the performance is going to be fairly set, and some team actually need to add some more, like a takeoff and landing is going to be more important for SAE, but other teams may not. Other team may need to have like a range and endurance, power of gliding. Lots of concentrated performance requirement to begin with. You need to kind of show that your airplane design satisfies those kind of things. But I'm going to cover what kind of a performance I'm expecting by showing unit C5. So come to think about next week and another week, then following week is the final week, right?
No, it's the following week.
Following
2 weeks.
2 weeks, yeah, that's right. So next week is not the final week, but after that, it's going to be final week.
No, the final week's after that next
Okay.
week.
Really?
We have 2 weeks left.
Hold on.
We have 2 weeks left.
But the final week, you don't want to do anything because you have an exam on Thursday.
Yeah.
So Tuesday, you probably want to secure it as a study day. That's what I guess. In other words,
Sure.
because exam 2 is practically speaking your final exam for this class, because your final is a final presentation, right? So final week Tuesday, I really want to set it up as a study day. So maybe Tuesday of that previous week.
Wait, so next Tuesday?
I don't know. I don't know what I'm even talking about. So just to
When
tell
you
me,
say- That means next Tuesday.
next
if that's
Tuesday,
fair, according to you.
according to me.
Next Thursday.
Yeah, that's what I said. Next Thursday would be better.
Next Thursday.
So this is this week, that's next week, that's the following week, well,
And
that's the
when
final week.
starts.
So this Tuesday class, I want to set aside as a study day for you guys. You really want to study for this exam too, because this is practically speaking, it's a final exam. And also at the same time, your presentation is Monday, right?
Cool.
Yeah, so you really want to kind of free up the final week because you have other classes taking and then demanding.
What time is our final scheduled for on?
Final is Monday.
What time?
10:15 to 12:15.
Yeah, 10:15 to 12:15, Monday, May 3rd. Okay? Yeah, so this is the final presentation, phase 4.
Is that gonna be online through Teams? Or is it gonna be in person?
It's gonna be here.
Yeah.
Final presentation.
It'll be here.
I think it,
Can we just be in class?
I don't know. I haven't decided yet, but it could be better to do online because you want to show your desktop. Yeah, because
Can we
that
just show
could be
it
easier.
there?
Or you can show it from here, of course, yeah, but either way is fine. It's up to your preference. I can do either.
It's a lot easier when you have all 3 members in the same room trying to do a presentation
Yeah, that could be. So your preference is what?
in class.
In class. Do you have any other comments, online people? Do you want to do in-class presentation or online presentation? I want to hear that. Any preference?
I'm good with either. I think possibly online presentation might be easier for like
Yeah, okay.
presenting like your resources. You can kind of go at your speed and make it a little easier.
Yeah, I thought that too. In other words, since you're doing, you need to, yeah, but it's PowerPoint, isn't it?
Yeah.
Yeah, so PowerPoint means you can present in class or online. I think it's the same thing.
It doesn't matter.
It doesn't, yeah, it doesn't matter. Yes.
I just found it easier.
Yeah.
this last
So
time.
just let me know if you have a strong preference. Just let me know. But the temporality right now, as of today, let's just try for in-class presentation right here in this classroom. Okay. I hope it's okay, David. Right.
Sorry, I didn't hear that. What?
Yeah, temporality as of now, we are trying to do in-class presentation on Monday because it's just a simply PowerPoint presentation.
Yeah, that's fine.
I'm not going to ask you to, hey, show me your actual X-Flyer5 simulation kind of thing. I'm not going to do that.
We can
If I do that, it's probably better off doing online presentation, but I'm not going to do it. So, okay. Any comments, anybody? Please just let me know, okay, anytime. So temporality, Thursday next week. That's the phase 3. That sounds like only option. Because following week, Tuesday, you don't want to do anything, you want to study, right?
You can make it do that Tuesday
Eh?
in the morning. Because then I don't know if anyone else,
Okay.
like Thursday is fine, but
Okay,
if we wanted more.
okay. So that means you push back yourself to the edge so that there's no room to extend.
Yeah.
That's what
let's
you're
not do that.
that's what you're talking about.
Let's not do that.
Eh?
For now.
So that means if I say it's due Tuesday period, I cannot push back, it's impossible.
Can we just have it then? We just have the tentative due date be Thursday. And
Tentative Thursday morning, and then if multiple people request, I may possibly push back to Tuesday, but I have a right to reserve to say no, the heck no. I'm not gonna push back. I can possibly do that. The professor may backstab you at the very end, I don't know. You don't assume anything. You assume too much sometimes. It's a Star Wars, somebody said it. You assume too much. Well, that's a bicycle, isn't it? Bicycle is like a modeled after Japanese, isn't it? That's a Japanese accent. It's a Star Wars bicycle. You assume too much, princess. Anyways, that's, yeah, you have to. So temporarily Thursday morning, is that okay? Is that okay? Temporarily Thursday morning, okay? All right, let me do that. Okay, so where am I? Let's just move on. Okay, so today we are going to take a look at Unit C5. Okay. This is just a bunch of examples of performance calculation. So today's example is essentially completely making up a foundation of your Phase 3 project. Oh, by the way, SAE team, Phase 3, Phase 4 are required. Okay, Phase 1 and Phase 2 is optional. Those are optional because you pretty much did it in L. Okay, so if you don't turn in Phase 3, you get 0 score. Okay, be careful. Phase 4, of course. Okay. So C5 is a performance analysis examples. I'm going to show you F16 performance analysis. This is actually continuing from Unit C. Okay. Yeah, so you are going to refer back to lots of aerodynamic data back into Unit C, which is, which unit? Let me double check. Okay, so you have to refer back to what you did in the previous unit. Some kind of exercise B3. That's right. So lots of information actually trickle down from Unit B3 right here. So Unit B3, as an exercise, you actually did computation of F16 whole aircraft analysis. This is partially done by X-Flyer 5, partially done by your hand, and actually you compare together. Compare each other. This is the hand calculation results. This is X-Flyer 5 results. You did it and then reported on Phase 2B project. Okay, so this is based on Unit B3 F16 whole aircraft analysis. Okay, so lots of aerodynamic information is coming from here. All right. So this is based on B3, which is aerodynamics. Okay. Then after that, I'm going to today just to do some example, which is quite interesting example, flight test and then PS determination. This is actually can be done in actual airplane. So out of those different project teams in this class, who is actually planning to really build the airplane that you desire, that you design? Do you have a plan or a desire to build the real airplane out of this X-Flyer 5 design project throughout this semester? Please raise your hand. I expect at least one person's hand raised. Listen, please raise your hand if you plan, if you have to build a real airplane based. Okay, thank you. So this example or exercise is basically targeted for that kind of situation. Suppose if you are using X-Flyer 5, do all sorts of analysis and come up with your final design and then put that design, give it to your manufacturing team, and the manufacturing team come up with a prototype. then you can actually apply this technique to determine actual drag product values, actual PS, which is excess power determination. Suppose if that airplane comes with power plant, and then you can actually conduct the testing of level flight, constant speed, or constant speed climb, like a gliding, power plant cutoff, power off gliding. You can conduct that kind of actual flight test. Very simple one, something doable. It's not complicated flight testing, professionally done. You can actually build your prototype and conduct very simple those flight testing and then confirm your results. So this could be fairly interestingly important for SAE team as they come back from summer. In fall semester, you basically said you're going to actually build your airplane, right? Cool, let's do this. And then if you actually successfully build and then compare and then flight test and then compare the results and confirm, that is going to be worth for public publication, AIWA or SAE, either way. Okay, so that's what I'm thinking. Okay, not necessarily I'm trying to push you to the edge, no. You can do whatever you can, but this is going to open up the opportunity for the entire team, all right? That's why I'm trying to entice Jimmy to join in, but he refused to join. Right? Do you want to join? It's not too late now.
No.
Join SAE for phase 3, 4, that's fine. Your answer is still no?
I don't have the time for it.
The,
And I won't be here for a long time, so it doesn't show any benefit.
you can squeeze out your time. Anyways.
Not next semester, I can't. I can right now.
Next semester, yes?
No, because next semester I have capstone.
Yeah. Well, turn this into capstone. I don't know. Maybe. Okay, we can talk about that.
Sure, we can talk about it later.
So let's just take a look at the F-16 performance analysis, okay? So this is, again, everything, you know, this is the geometry and also aerodynamic data is coming from B3, okay? So based on the unit B3, I'm going to continue showing this is a performance example of F-16. So first of all, starting point here of a performance parameter analysis is you're going to come up with for takeoff condition. In other words, if your airplane comes with a flap 4 down, you're going to run X-Flyer 5 simulation for a takeoff very low Reynolds number configuration with whole airplane, but flap 4 down, and then find out maximum CL for the takeoff configuration, and then maximum CL for the landing configuration, okay? It could be the same, could be different. In this case, it's different because for takeoff, F-16 is not gonna take off with flap 4 down situation because you have a powerful enough engine. You don't need to do that, okay? But for landing, of course, you have to do a flap panel 4 down. Also, leading edge is going to be also down too. And because of that, you're going to increase the CDO. CDO is pretty high, okay? So this is a landing configuration, takeoff configuration. You need to come up with those information from X-Flyer 5 to begin with, okay? And then after that, since this is a supersonic capable airplane, you are going to construct the drag polar calculation based on table 5.5. This is a drag polar. Now, most of the teams, you don't need to probably do that. This is the supersonic airplane, so this is the transonic to supersonic flight range. You have to compute CDO and K1. So this is a drag polar, including subsonic, transonic, and supersonic range. Of course, transonic to supersonic, you have to include additional CDO component, which is the wave drag. So CDO is going to massively increase. Why is that? Because of the wave drag. Okay. If your design is a supersonic capable airplane, you need to do this. Now, most of you probably don't need to. That means you're going to pick up your drag polar data from X-Flyer 5 as is. Okay? So that's what it is. The next step is, of course, you need to determine your power plant. This is a turbojet engine. Well, this is turbofan, low bypass ratio, right? So this is F100-220 Pratt & Whitney. Okay. So you have a catalog spec of C-level installed thrust. Important things, installed thrust. If the catalog spec only provides you the static thrust not installed, you have to kind of estimate a certain percentage taking off of the available thrust at the sea level to begin with, okay? And then if the catalog provides you installed thrust, you can go with it. And this one actually comes with afterburner, so you need to have a dry, which is no afterburner, and then wet, which is with afterburner. Oftentimes, this is called military power. This is afterburner. Military or dry, which is basically you're not going to use afterburner. So you have to have two versions, with and without afterburner condition, TSFC, and also thrust available. Both, okay? Once you are given C-level value, you can compute TSFC and thrust available for a given altitude by using either multiply by square root of temperature ratio or speed of sound ratio, either way. This is the equation coming straight from, I think, Unit B1, okay? And then this is going to, okay, up to here, this is going to lead you into making up this plot, right? Yeah, this is a thrust available, thrust required plot for turbojet, turbofan engine. If you have an airplane with a propeller, this is supposed to be power available, power required plot. Okay? So if you are designing a turbojet, turbofan engine, I would expect two plots. One is a thrust plot, the other one is a power plot. If you're designing just a propeller-driven airplane, I think the single plot of power will be required. Okay, so this is required for your phase 3. Don't miss it. This is the very important plot. Without it, I have to take massive points off. Probably at least, like, I don't know, minus 50% without this. This is something super important. Okay. Now, obviously, if you have afterburner, you have two thrust available. One is a dry, one is with afterburner. This is thrust required. Essentially, this is just a drag you computed from X55. Okay. So anyways, this is absolutely required out of those information here. Okay. The next thing is, of course, you have to figure out how much total weight for takeoff configuration. So payload is important. Of course, SAE team, you guys have payload, of course. And then what kind of materials you're going to choose now come into play now. Okay, so your airplane's design is getting closer and closer to something you really want to manufacture. So this is going to determine takeoff gross weight. Okay, now this is going to lead you to compute like a center of gravity, but center of gravity is not required at this stage because center of gravity is required only if you want to find out the stability. So this is going to be important at phase 4, but not phase 3, at least not yet. Now, phase 4, you literally seriously find out center of gravity location and also correspondingly, where is the neutral point of this this entire airplane for each configuration if you come up with a different configuration. Because that is going to either make your airplane stable or unstable. Okay, that is going to be a major thing you're going to do in phase 4. All right, and the next thing is if you have constraints such as supersonic turn, climb, and other things, you need to come up with a maneuver weight. This may or may not be your constraint. Okay, most of the airplane you design actually come up with a takeoff weight. That's all, and then you don't have to maneuver certain things. You may have a maneuver requirement, but it's not probably like a 9G, like a Mach number 0.9, because that's a jet fighter. Obviously, your airplane may not be. Okay. So this is like optional. And then fuel weight. If your airplane is designed for long range, this is important. You need to somehow compute how much fuel do you need, and then where do you put that fuel tank integrated within your configuration. That is going to affect on your CG. and your range. Endurance also, big time. Okay, so those are the things that you need to start thinking about and then integrate within your X-prior model. Okay. Next thing is, first of all, glide performance. This is basically take off and then cut off your engine and then act as if you're a glider. This is going to be maximum glide ratio, which is maximum L over D. This is kind of easily found using X-prior path. Okay. This is maximum L over D. Once you find the maximum L over D flight condition, that is going to be a maximum or best glide range or maximum glide ratio. Either way, it's the same meaning. Okay. And the next step is, okay, so what is the corresponding glide speed for the best glide range? Condition is CD always K1 CL squared. Do you remember this? Actually, I don't remember those, so I have to always go back to my summary. Let's just go back to the, not the arrow. Let's just go back to unit C2. Okay. I always want you to bring you back to the summary page. Summary page. Yeah. Let me tell you something. I created this summary just for you this semester. Last semester, I didn't provide this kind of summary for anybody. And then you can never find this summary at any other location, including Air Force Academy, the original authors of this textbook. This is super useful, at least for me. This is a lifesaver. Okay? This is important. So let's just take a look at it. Power of glide, maximum endurance condition is this. In other words, minimum sink rate. This is the best glide ratio. Okay. If you get confused, always go back to this page. Okay. So now, that's where it comes from. So this is the for the best glide range. This is the condition. This is the minimum thrust, essentially. Okay. Then from here, you're going to determine the airspeed corresponding to the best glide range. Okay. I'm going to compute that. Next thing is, what is the minimum sink rate? This is the condition for minimum sink rate. And then corresponding airspeed for minimum sink rate you can determine. Okay. And then this is the sink rate itself. Again, condition is starting point is here. So this is the condition for minimum sink rate. You're going to pick up this condition to come up with the minimum sink rate. So you're going to compute all of those things. Okay. Then compare against your initial requirement. Does this design actually satisfy your initial requirement? Or even though this is not the requirement, you can actually find out, okay, this is how much airplane can perform. Okay, either way. Next is the climb performance. Obviously, if you have afterburner, you need to consider the thrust available with afterburner on and off. Okay, so one is dry, one is wet. Okay. So best angle of climb in military thrust is L over D maximum. This also depending on the altitude. So you are going to compute with several different altitudes. In other words, if you're designing transport airplane transonic, you need to set up your cruising altitude, optimum condition. You want to optimize your performance for that given condition. Okay. So this is the condition for the best angle of climb. This is the maximum L over D. And then you're going to compute the thrust available. And then this is the best angle of climb. Basically, this is a flight path. 17 degrees is the best angle of climb in this case. Okay. And then maximum rate of climb. This depends on how much excess thrust do you have. Thrust multiplied velocity is the power. So this is essentially how much excess specific power do you have, and it's going to determine rate of climb. Okay. So this is the specific excess power. That's what you're talking about. Okay. This is going to determine the maximum rate of grind. Okay. Next is, of course, rotor and cruising performance with engine on. You already did engine off performance, grinding, but this is rotor and cruise performance, endurance, and the range with the engine on. This is the case for turbojet. So you're going to look at this. This is the condition for maximum endurance, maximum range. If you are propeller-driven airplane, it's a different condition. Let's be careful. In other words, if you're propeller-driven condition, power of glide and then cruising range and endurance are essentially the same thing. You don't have to calculate twice. Since this is a turbojet turbofan, you're going to compute power off case and then engine on case. Those are different conditions. Okay, let's be careful about that. So if you're designing jet engine airplane, you need to have two plots. One is a thrust, one is a power. If you're propeller-driven airplane, it's essentially power only. Okay, and then power off glide is essentially the same as power on performance of endurance and range. Okay, so those are the small things that's coming from the previous units. Okay, so you're going to either simplify the average method or aggregate endurance and the range equation to come up with actual range and endurance. Some of the teams, this could be super important, especially if you're designing long range transport or some kind of airplane, just like that. Okay. All right, so next page. This is the maximum range, obviously a different condition. Okay, so this is a turbojet engine on situation. So maximum range, you have to accelerate. Okay, so this is the cruising maximum range. It's not the power off maximum range. Those are different since this is turbojet engine. Okay. And the next thing is that you really want to find out specific excess power if your airplane requires maneuver. Who is the sport airplane? Somebody is designing sport airplane. This is probably the most important factor, right? So what is the maneuverability? That actually requires you to know how much excess power do I have. This is super important requirement. If you skip all of those, you're not going to call your airplane sport airplane, okay? Because you didn't show any evidence for it. So this is quite important based on your design purpose, okay? So you are going to set up certain things, such as in this case, this is the fighter jet. You need to have a sustained load factor 9G at Mach number 0.9, altitude 5,000 feet. This is very, very severe requirement. Requires a lot of strong materials and lightweight and lots of other things need to come together. But at least in terms of specific excess power required for such a maneuver, you need to come up with the value. Okay? That is this. So this is a specific excess power 803.5 feet per second at altitude 5,000 feet. This actually requires a huge engine, isn't it? Okay. So this is going to actually feed back to your design and then say, okay, well, we chose the engine which is not powerful enough. I'm sorry. So I gotta pick up a bigger engine. That actually bigger engine requires bigger body. Well, that means, well, we have to recalculate the aerodynamics and then make the wing bigger. Well, that actually making it heavier. Well, structures guys start to complain, well, we need to beef up the airplane. You know, we have to add this brace and this spar and here and there. And then, oh, by the way, I have to mount a bigger engine here. So the engine counting is bigger. Then aerodynamics guy says, well, that's actually increased the CDO. So hopefully your team is not going to get into that downward spiral internal battle. It's avoided. You have to compromise. Okay? So if that kind of internal battle starts to happen, now is the time, before the phase 3. So be ready for it. Okay? So specific excess power, you need to compute. Now, suppose if your team realizes, wait a minute, this engine is not powerful enough. Man, this is a problem. That's okay. You just provide that kind of issue as is. I'm not going to necessarily point you down. Once you discover those things and address the issue, that's probably good enough to meet the purpose of this class. This class's purpose is to design a beautifully optimized airplane. No, this class's purpose is for you to understand what is the required process. This is the big problem I encountered toward the end of the semester. Don't go panic, just report it, okay? I'm not going to necessarily take huge points off for that, as long as you recognize and report nicely. If you try to hide it, if I discover it by myself, oops, that could be penalized depending on my mood. Okay, don't try to hide anything. If you discover something interesting, report it. Just be honest. Okay. All right. Next one is oh yeah, takeoff and landing. This is huge for SAE team, isn't it? Because your airplane is all about takeoff and landing. Okay. So this is something you have to cover. Okay. And there are some teams, you have a strong enough thrust, takeoff and landing is not an issue at all. That could be. I guess you can actually try to do constraint analysis to find out if that's your case or not. You can quickly do that, okay, because you know how to do it from quiz 5. Okay. But obviously, some teams, you cannot avoid this. And then other things you can add if you want to. Okay, so the performance requirement. Okay. So this is pretty much a basic performance requirement I'm expecting you to report in phase 3. Based off of your design of X-Flyer 5, you come up with some kind of airplane. And then how much performance you can expect from that airplane. That is phase 3. Okay. Now you can possibly discover, hey, this airplane doesn't meet up at all. This is a crap. It could be, but please report that. That's fine. Okay. And then as long as you can discover what was the issue, yeah, I'm happy with it. Maybe we've been ignoring the structures. Maybe we've been too optimistic about engines being too weak. It could be. I don't know. It could be any issue, but please report that. If you discover those things and then you can detect and report nicely, that's good enough. Okay. Any question? So you may end up realizing, hey, canard for sport airplane, I don't know if it works. I don't know. If so, yeah, please report it. Don't hesitate. Or you can basically compare side by side conventional configuration versus weird canard configuration. What's pros and cons? That's fine too. Okay. Performance-wise, this is way better. This sucks. That's fine too. So this is your practice. In other words, this is a software. If you know how to use it, it's a huge appeal point if you want to get a job of airplane design. This is a software actually I learned from Boeing Skunkworks people recommended this as a part of the education at this school. That's when I started using this software. Okay. Before that, I didn't even know this software. I doubt if any other aerospace engineering major capable school actually providing this kind of education or not. I'm not sure. Okay. So this is your prime opportunity. Just run as much as you can run. And then SAE team, we can talk about this. This could be interesting fall semester activity. After you design airplane using X-Flyer 5, manufacture it, and then let's do a flight test. Okay. So let's just take a look at page 6, flight test / PS determination. Okay. So this is a simple glide testing, and then by doing this, you can actually determine a drag polar. This is a flight test. It's just a mono airplane. Throw it in I don't know, what's the big room of this school? No, I mean some huge building you can fly airplanes.
Gym, DLC.
Gym, something like that. So you can do this and inside of the huge building so that you can do a flight test gliding, just gliding, okay? And then what you can determine, I think direct port, okay? So flight test, I'm talking about the actual manned airplane. Flight test, it needs to be conducted. Most of the flight test is a very simple, very boring, repetitively boring test, such as airplane takeoff, level flight, constant speed, or constant acceleration, level flight accelerating flight, repeatedly with different altitude. Very boring test. Day in, day out, test pilot need to do such a thing, okay, to determine certain characteristics. Or also, it could be just a simple constant speed climb from this altitude to that altitude. And then level flight, okay, let's do another constant speed climb from this altitude to that altitude. It's called sawtooth climb. Very boring test. But those are required. Or it could be glide testing. Cut off the engine, just to glide off from this altitude to this altitude. And then time it, and distance required, that kind of stuff, okay? So let's just take a look at flight test here. So once an aircraft is designed and built, the manufacturer must test it to ensure it meets or exceeds the customer's requirement, of course. Then flight test oftentimes is more mandate. Test pilots spend hours and hours and hours flying straight and level or making level turn or level acceleration in order to validate all the estimates and predictions made in design. This is very, very boring process, I would say. It's nothing spectacular. It's just a level flight day in, day out, take the data out kind of testing, okay? Now, one of the important tests is flying the performance limits specified by the customer. That means what is the maximum speed, maximum climb, and other things. But that's kind of one-time deal, okay? The flying to the edge of the envelope, this actually happens, okay? But this is quite risky, so they're not going to do it on day one. They test it at the very end after developing lots of flight tests and then fix and then bug fix, and so that now it's safe to push all the way to the envelope limit. That is not going to happen easily, okay? Another essential test is glide testing. This is something you can do, SAE, okay? All right, so this is a glide test to determine direct port. So you're going to, you don't need the engine. You're just going to make it fly in a big room like a gym, and you're going to determine the position and the time. And then you're going to determine L over D, which is equal to a range of altitude, which is you can optimize for the optimum glide range, okay? So next page. Let's just take a look at the small balsa wood glider testing. So you can do this all the time. But by the way, when Dr. Ashworth was teaching this class, this was the final project, by the way. Okay, so he actually made everybody taking this class design and build balsa wood glider and then conduct this test to determine direct port. Okay, now obviously this is quite interesting. If you write hands-on, too bad I'm a computer geek, so I basically, I'm attracted more to using software, do everything in front of computer. I'm lazy, I'm not the hands-on guy kind of person. But this is quite interesting, and then you can of course do it, okay? A small balsa wood glider was flown at the different glide speeds. The results are given in this table, okay? So this is conducted like a total 6 flights. Everything is launched from 30 feet, and then distance is 100 to 160 feet, depending on the glide path angle. Obviously, you can launch it like a glide path angle 0 to like a steep And then you can change the distance, and then you can measure the time to landing, and the flight distance also, and then you can measure the true airspeed. Now, one questionable thing is, how can I determine this? This is going to be probably in ultimate solution is you want to come up with a compact pitot-static attached to your airplane glider. And then with a transducer attached, you can sort of determine as you fly your true airspeed, okay? You can possibly do that. Or a GPS device attached to your airplane, I don't know. So this is kind of questionable, how can I do it? But the rest of it is pretty easy, okay? Then you can plot drag coefficient, lift coefficient out of those total 6 flight, and then you can actually plot it and determine drag total. Very simple, okay? So you're going to go through the details, okay? Yeah, I'm not going to cover that, okay? So this is the step-by-step process of determine drag total. So once you purchase your own airplane or build your own airplane for competition, you can do this test easily, okay? Since you took this class, you are the only member of SAE who took this class. I think you are the only person who can do this. Okay, good. Then you can hire a bunch of freshmen and let them do all the manual labor work. Data taking and flight and fixing, all other things. You are the only one who knows what you're doing. All others are manual labors. That's probably a typical situation, that's fine. Wait until those freshmen, this is up to your level. And back then, during that time, you already graduated. Then after you graduate and get a prestigious job, and then you come back on October with trying to hire someone. I'm not kidding, because that's the pattern ongoing. Every fall, one of my graduates come in and always ask the same question: do you have any good graduates? I want to grab someone. My team needs someone who can be like an instant, contributor for our team. Question is, do we have that kind of person? I really want to say, sure, of course, we have a list of 10. The reality is,
Yikes.
So again, it's all up to you, all right? So again, this is the opportunity for you to grab as much information you can get. You can appeal to those people who come in October with saying, hey, this is the computer simulation-based airplane design I conducted with Dr. H. This is the flight test results. By the way, this is a paper associated with, you get a job. You get a job instantly. Think about that. Okay. That's true, yeah. Okay. So last page of Unit C5, let's take a look. Example C5-2. So this is how to determine specific excess power PS by doing simple flight test. Okay. Obviously, this one requires airplane with installed power plant. So suppose if you conduct like a level flight, and then try to accelerate without gaining altitude, or sawtooth climb. In other words, from this altitude to this altitude, you try to climb up with constant speed. Very boring test, but it is going to determine specific excess power. Let's take a look. An aircraft performing sawtooth climb executes a climb from 9,000 to 11,000 feet on a standard day, yes. If the climb takes 50 seconds, what is the aircraft's PS, specific excess power, at 10,000 feet, and the flight conditions of the test? Assume true airspeed was constant during the climb, because it's sawtooth climb. Okay, so let's just take a look. So this is the equation to determine specific excess power for steady climb. This is a level acceleration, so this is sawtooth climb. So this is level acceleration. Okay. So simply, you're going to apply these two equations to determine PS, okay? Once you determine PS out of those very simple, very boring test flight, what's the result? You are going to provide PS diagram, okay? The contour of PS for a given different altitude and all that. That is so useful. Because by looking at the PS contour diagram, you can tell how fast your airplane can fly for certain altitude, and then how much you can climb up, how much seating you can reach. Those kind of important information can be given from that table, right? And also that is going to determine your flight envelope. Okay. So for the steady climb, if it takes 50 seconds with the constant speed to gain 2,000 feet of altitude, this requires specific excess power of 40 feet per second. Very simple computation. Second one, an aircraft performing a level acceleration accelerates from 295 to 305 knots in, what's kias? Knots in,
Indicated airspeed.
eh? What's kias?
Indicated.
Yeah, indicate, so yeah, that's right. K-I-A-S. A-S is airspeed, sorry. So knots indicated airspeed, oh, okay. Holy cow, only indicated. So that means you have to convert. So indicated to what? Calibrate, calibrate capital. Indicated to calibrated equivalent lowercase to the true. So you have to go through this process once kias is given. Too bad. Anyways. So 295 to 305 kias in 2 seconds at 10,000 feet on the standard day. Well, of course, you're given this is a position error. Position error makes kias to kcas calibrated. Then by multiplying F factor, it is going to make it equivalent kias. Okay. And then if you know the actual density of the flight altitude, multiply square root of density ratio is going to get you true airspeed, ktas. Okay, so you have to go through this process anyways. By the way, this conversion process of airspeed can easily be included for exam 2. Be ready for it.
Are you gonna make us do?
If I want to.
Could you not?
Well, this is something you probably need to do anyway.
Just once. Just do it
Yeah,
once.
well, it's easy, isn't it? Everything is given.
Yeah.
If I make you do this, I give you, of course, delta VP, I give you F factor, I give you the density, actually OAT. You can do it easy, okay? But
Don't give us a clue.
this could be included exam 2, okay?
Stupid problem to get it 3D, just for
Yeah.
feasible.
Not really, take a look at it. Not really. Okay, so first convert kias to true airspeed through ICD process. 300 kias plus delta P, kcas multiplied by F factor gets you equivalent multiplied by square root of density ratio gets you ktas. So this is a conversion process. You can do it, of course. Finally, you want to convert into feet per second. Holy cow. This could be an easy MATLAB program. In reality, of course. Yeah, well, you can create a MATLAB, like, I don't know, short code to compute. So this is kias, this is delta P, what is the feet per second kind of thing, okay? I don't know if I want to do this for second exam. May or may not, I don't know. But I hope you know it. This is important. Okay.
If you give us MATLAB, we can do it.
That's a good argument, okay. That's a good point.
Yeah.
Great.
Just give MATLAB.
Okay, so yeah, but bottom line, this is quite important. So I hope you know how to do it, okay? Not necessarily I want to test it in exam 2 because this is just a time-consuming conversion process. Okay, so now from here, delta B is given. So for level acceleration, you are just going to plug in dBdt. This is an important thing. So this is delta P over delta T. This is 175 feet per second, specific excess power required to accelerate in level flight. Okay. Any question here? So this is a very simple example for PS determination and also direct polar determination for glide testing. This can be fairly easily done. You have to, of course, coordinate lots of things, but this is something you would probably want to think about in fall semester as the team member comes back. And then if you do this process and compare against X55, this is probably a good enough material for professional publication. Okay. All right. Any question? By the way, David, aren't you an AWA guy? Who's actually?
Yeah.
Yeah, who's actually AWA? Oh, okay. So you guys are AWA. Are you? What kind of design you have a sport airplane? Okay. Do you actually plan to build one?
Yeah. We've made a bunch of prototypes already. Yeah.
Oh, that's good. That's good. So you can actually also, at the same token, you can apply this technique, right? And then let me tell you one thing. We have an AIAA student conference, which is every year, Region 6 conference happens. So if you actually apply this kind of technique and then compare against the computer simulated design, which is X55 and all, that could be a interesting, at least student conference paper. It could be like a professional AIAA paper too. Okay. So just if you have a desire to continue on and push it before you graduate, let me know. I can squeeze out some resources from College of Engineering to support you if you want to challenge for the publication for it. Okay. It's up to your motivation. All right.
That could be cool.
Okay. Good. By the way, do you see anybody from Aero want to ask you a question? You're a tutor.
Nope. No one has asked. No one has requested a session yet.
He lied.
Okay. Damn it. So that means okay. Well, you have no excuse. I even hired you tutor, and you never used tutor. So F is F, you guys. Aero students. There are lots of students actually say, well, we need a tutor to pass this class. And you never show up.
You don't even use the tutor.
Anyways, so that's it for today. Do you have any question? So on Thursday, we are going to move to Unit D, which is stability analysis, okay? All right, so you guys probably need to start working on phase 3 of the project, which is tentatively due what? Thursday next week.
Yeah.
Okay. Okay. So hopefully you're not gonna scream in last minute. All right. Have a good day. See you guys on Thursday.
Phase 3 super essays. I could see him doing stuff.